2-point charges are placed on the x-axis as follows. Charge Q1 equal plus 5 nanocoulombs is located at x equals 0.1 meters, and charge Q2 equals minus 4 nanocoulombs is located at x equal minus 0.3 meters. A. A charge Q3 equals minus 6 nanocoulombs is placed at the origin. What is the net force exerted on the Q3 charge? And B. Where should the charge Q be placed such that it is in equilibrium? Only charges Q1 and Q2 are present. Let's start with part A of the problem. We have three charges. Charge Q1 placed at 0.1 meters with respect to the origin. Charge Q2 placed at minus 0.3 meters with respect to the origin. And charge Q3 negative, the same as charge Q2, placed at the origin. Charge Q1 is positive. We need to find the net force exerted on the Q3 charge. Charge Q1 will exert the force on charge Q3, and charge Q2 will exert the force on charge Q3. Because Q3 and Q1 are of opposite sign, the interaction force between them will be attractive. So the force applied by Q1 on charge Q3 will be oriented towards Q1. Q2 and Q3 are both negative charges, so they repel. The force applied by charge Q2 on Q3 will be away from the charge Q2. As you can see, in order to find the net force acting on charge Q3, we basically need to find the sum of these two forces. The problem gives us the charge for each one of the three particles, and the distance between charge 1 and charge 3, and the distance between charge 2 and charge 3. Remember, charge 3 is at the origin. The net force acting on charge Q3 will be nothing else than the sum of the force applied by charge 1 and charge 2. Each one of these forces can be calculated using Coulomb's law. And because they are oriented in the same direction, remember forces are vectors and you have to take into consideration their orientation, all you have to do is add up their magnitudes. So the net force will be given by the force applied by charge 1 on charge 3, which is K, electric constant, multiplied by the product between the two charges, Q1 and Q3, and divided by the distance between them squared. And this expression represents the force applied by charge Q2 to charge Q3. All we have to do is replace the given values in this equation. If you look at this equation, you see that the electric constant K and charge Q3 appear in both terms, so we can factor them out. And we have then that the net force equals, the electric constant K is 9 times 10 to the 9. Charge Q3 is 6 times 10 to the minus 9 coulombs, and I want you to see that I have not replaced the charge with its sign. I have already taken into consideration the fact that Q3 is a negative charge when I drew the direction of these forces applied by charge Q2 and Q1. So when you replace the charges in the Coulomb's law, in the expression for the electric force, you always replace them with their magnitudes, and you have already taken into consideration what type of charges are by looking at the direction of the force. Multiplied by, this is charge Q1, 5 times 10 to minus 9 coulombs, divided by the distance between charge 1 and charge 3, which is 0.1 meters squared. Plus, and this is charge Q2, once again you see it doesn't have a minus sign, it's just 4 times 10 to minus 9, divided by the distance between charge Q2 and Q3, which is 0.3 meters squared. All you have to do is use a calculator, and you get that the net force applied to charge Q3 is 29.4 times 10 to minus 6 newtons. Now for the part B of the problem, you need to find the position where you can place a charge Q such that it is in equilibrium. In this case, you have only charges Q1 and Q2. We don't even know what type of charge Q is, positive or negative, but it doesn't really matter. You will see that very soon. Now let's imagine that charge Q is placed somewhere in between Q1 and Q2. In this case, if charge Q is a positive charge, then there will be an attraction force between Q2 and Q, and the repulsion force between Q1 and Q. So the forces applied by charges Q1 and Q2 to charge Q are both oriented in the same direction, which means that there is no way for the charge Q to be in equilibrium when placed between charges Q1 and Q2 because the net force cannot be zero. We need to place this charge Q outside, either to the left of Q2 or to the right of Q1. Now the question is, where should we place it? Well, Q1 is 5 nanocoulombs and Q2 is 4 nanocoulombs. Since the force is directly proportional to the charge, it means we have to place the charge Q further away from Q1 and closer to Q2 in order to make the two forces that these two charges apply to the charge Q balance each other. So I am going to place the charge Q to the left of charge Q2, and I'm going to consider again that it is a positive charge, it doesn't matter. And then there will be an attraction force between Q and Q2 and a repulsion force between Q and Q1. These two forces, F1 and F2, are oriented in opposite directions, and their magnitudes have to be equal in order for the charge Q to be in equilibrium. I will choose the zero of the coordinate system exactly at the position of charge Q. That means that the distance between charge Q and Q2 will be unknown, and this is what I need to figure out, and I'm going to call that distance x. And the distance between Q1 and Q2 is nothing else than 0.1 meters plus 0.3 meters, which is 0.4 meters. And here's what the problem gives us. The charge 1, charge 2, the distance between charge 2 and charge Q, which is x meters, the distance between two charges 1 and 2, which is 0.4 meters, and the distance from charge 1 to charge Q will be x plus d. Now, in order for charge Q to be in equilibrium, the net forces acting on it have to be zero. In this case, the positive direction is to the right, and that means that when you write the net force, you have to take into consideration that force 1 is oriented in the negative direction. So the sum of the forces will be minus F1 plus F2 equals 0, or F1 equal F2. Basically, the two forces have to cancel each other out. Using Coulomb's law, we can write the expression for each force, and we have that the force applied by charge 1 to charge Q equals K, the product between the charge 1 Q1 and the charge Q, divided by the distance between them squared. And this is the force applied by charge Q2 to charge Q. As you can see, we can get rid of the electric constant K, and we can also get rid of the charge capital Q. They show up in both terms. And that is why it doesn't matter what type of charge Q is, positive or negative, you're always going to get rid of it. We are left with Q1 over x plus d squared equals Q2 over x squared. Now what we do, we cross multiply this, and we get Q1 x squared equals Q2 times x plus d squared. We square the parentheses, and we have Q1 x squared equals Q2 multiplied by x plus d squared is x squared plus 2dx plus d squared. We open the parentheses and rearrange all the terms such that we have something equals 0. So we bring all the terms on the right to the left side of the equation. And then we have Q1 minus Q2 multiplied by x squared minus 2Q2 dx minus Q2 d squared equals 0. This is a quadratic equation, and the result is the position of the charge Q with respect to charge Q2. Now, in order to solve this quadratic equation, we are going to replace everything with what the problem gives us. But I want you to be careful. Once again, when you replace Q2, you do not use the negative sign for the charge. You have already taken into consideration the fact that Q2 is a negative charge by considering that the force between Q and Q2 is an attractive type of force. So when you calculate Q1 minus Q2, you will have 5 nanocoulombs minus 4 nanocoulombs, and that would give you 1 nanocoulomb. So we have 10 to minus 9 x squared minus 2. Q2 is 4 times 10 to minus 9 coulombs. The distance d is 0.4 meters x minus Q2 is 4 times 10 to minus 9 coulombs. The distance d is 0.4. Don't forget to square it. As you can see, we can simplify the entire equation with 10 to minus 9, and we are left with x squared minus 3.2x minus 0.64. Use a calculator, and you will see that for this quadratic equation you get two results, a positive value for x and a negative value for x. From the way we chose the coordinate system, Q is at the origin, the only value for x that makes sense in physics is the positive value, because x is a positive distance with respect to the origin. And that value is 3.385 meters.